All right, good morning. Morning. Down there. I just looked at the schedule. We're supposed to get done chapter 6 and 7 this week. We'll be done today. So we're not behind. We should be right on course. So if we get done with 6 and 7 today, you can print out 8 and 9 is together, one learning guide. And that's ready to print out. Or load, whatever you do. Okay, and that's the last one. So we will probably get into that a little bit on Wednesday if we get done here at 6 and 7. So with that, how about quiz questions? 4. Yes. So on 4, let's see what we got here. All right, calculate the highest energy of visible light for hydrogen where the electron transitions from 6 to 2. Okay. So let's see. So I already put this in that this really is the equation. I think I've got it written out like this. 1 over n final squared minus 1 over n initial squared. But we know for visible light, it has to come down to energy level 2. Now to do this calculation, we're just going to flip our answer when we get all done, but let's do the right side here. So we got 1 over lambda is equal to 1.097 times 10 to the 7 meters to the minus 1. And I'm just going to square it right away. Well, no, I'll put it in. So this would be 2 squared, which is going to be 4, minus 1 over 6 squared, which is going to be 36. So now grab your calculator. And let's do your parentheses here first. So in your calculator, you should be able to go 1 divided by 4 minus 1 divided by 36. So take your calculator, 1 divided by 4 minus 1 divided by 36. And I got 0.222. Did I punch it in right? Okay. So do that first. Now multiply by 1.097 to the 7. So times 1.097 to the 7. And at this point, I get 243,777. So now we just got to take the reciprocal of that, because what we end up with now is 1 over lambda is equal to 243,777 point. Looks like it goes on forever. And that is meters to the minus 1. So then if we just take the reciprocal of both sides, or it's going to be 1 over this number, equals lambda 243,777.7. So if you have a graphing calculator, use your answer key down here. So I'm just going to take 1 divided by second answer. And that's to the minus 7 meters. So we got to get that in nanometers. So we get 4.10 times 10 to the minus 7 meters. Okay, what else do we have in this quiz? Yes. 5. Okay, so this, previously we considered the hydrogen electron transitioning from energy level 6 to energy level 3. That should be n equals 3 then, that's a typo. And actually, in question 4, it should be 2. Looks like I got a typo. It's we know that the energy of the electron in a level is given by E to the N, the level equals minus RHC over N squared. So the difference between the two levels is given by how much energy emitted when the electron moves from 6 to. So this is going to be absorbs. We should end up with a positive number, right? So this change in energy should be minus RHC times, and we said last time we have the result of that, right? When you multiply all that together, and right now it's escaping me what that number is. And this is going to be 1 over, it ends up at, it transitions from 2 to 6 to 2. How much energy? Oh, it's emitted. Oh man, oh wait, this one, I'm sorry, emitted. So we're going to end up with a negative answer. It's dropping back down. So it ends up at 2. So we're going to have 2 squared minus, it started at 6. What page did we work that out on from our learning guide? So I have the answer in joules per atom, which is what it's going to come out to, and I have it in, I'll kind of like it in kilojoules per mole. And let's see, this part right here is 2.179 times 10 to the minus 18 joules. So this will give us an answer in joules per atom. What else do we have? Okay, for 3, what do we got here? So for 3, yellow light has a frequency of. So here's our frequency. Red light has a frequency of. All right. Which of the following correctly describes the relationship between wavelength energy of yellow light versus red light? Which one's got the highest frequency? This is a bigger frequency, right? Not by much. So this has a higher frequency. Therefore, it has a lower wavelength. And it has a higher energy, right? Because energy goes with frequency. Energy goes with frequency. So this is yellow. Higher frequency, lower wavelength, higher energy. Something should match close to that, maybe. Because it would just be the opposite. This one has a lower frequency, it would have a longer wavelength, and it would have more energy. Anything else on this quiz? Okay, I think 6 and 7, and this quiz is Sunday night. Hopefully you poked around, maybe you're done with 6 and all, hopefully in 7 you poked around some. So we are going to today do quantum numbers right away. So that's going to be on page 18. So on page 18, so the Pauli exclusion principle. no more than 2 electrons can be assigned to the same orbital. We know that already, and we know that if there's 2 electrons assigned to the same orbital, they're spinning opposite directions. So if there are 2 electrons in the same orbital, they must have opposite spins. This leads to the general statement that no 2 electrons in an atom can have the same set of 4 quantum numbers, which is what we're going to do right now. And we also did Hund's rule. So quantum numbers are really, really simple. You'll just have to write this down. And this will be your guide for quantum numbers. So take this spot right here. It is best to just write this down. I don't have to write a lot of stuff, but I would write this down. So the 4 numbers is N, L, M sub L, and then M sub S. This is the energy level that it is in. And in the ground state, those numbers are going to be 1 through 7. This L is fixed. This is the sublevel. 0 for S, 1 for P, 2 for D, 3 for F. Now, M sub L is the exact orbital. And the exact orbital goes from minus L to plus L. And I'll show you exactly what we mean by that. If we have a p sublevel, how many orbitals do we have in a p? We've got 3, right? And it's really X, Y, Z if we are specific. Now, our sublevel is going to be a 1 for a p, correct? It's going to be a 1. So if the electron is here in this first one, this is a -1, this one's 0, and this is +1. The third number, again, tells us the exact orbital. If we do a D, how many different D orbitals do we have? 5, right? Then, if we are in a D to signify the specific orbital, this would be -2, -1, 0, 1, 2. And if we were in an F, one, 2, 3, 4, 5, 6, 7. It would go -3, -2, -1, 0, 1, 2, 3. So this third number would tell you exactly which orbital is in, right? Then the last number It's just a spin. Plus 1/2 or minus 1/2. Okay. Stay with me now for quantum numbers. Here we go. We're going to do the quantum numbers for all of these electrons. So first of all, for this electron right here, what energy level is it in? Energy level 1. The next number, the sublevel, is locked in. 0 for an S, 1 for P, 2 for D, 3 for F. 0, right? 0. The third number tells us the exact orbital. But that third number goes from minus L to plus L. L is the 0. So we don't do anything for an S. Minus 0 plus 0, it's still 0. And the spin with an up arrow is plus 1/2. What's the only difference in the quantum numbers for these two that are in exactly the same orbital? Just a spin, right? Energy level 1, 0 for an S, 1 for P, 2 for D. The only difference is the spin. Likewise, if we do this one, energy level 2. We're just taking that number right there, energy level 2, right? Energy level 2, sublevel 0 for S. It's in an S. The next number goes from minus L to plus L, minus 0 to plus 0. And the spin on this one is 1/2. If we do this electron, it is 2, 0, 0. Minus. Now, this ends in 2p2, right? If we did the electron configuration notation, 1s2, 2s2, 2p2. So if we do this electron, energy level 2. The sublevel, the next number, 0 for an S, 1 for P. So 1 for a P, right? 1 for a P. And then we go from, and we can label it, this is -1, this is 0, this is +1. And it's in the -1 orbital, right? The third one tells us the exact orbital. It's in the -1 orbital. And then it is spinning 1/2. Then this electron, energy level 2. Second number is 0 for S, 1 for P, 1 for P. The exact orbital it's in is a 0. And the spin is 1. Quantum numbers are clicking. Okay, let's do the ones down here. And then there's quite a few quiz ones. If you can do the quiz questions, there's a few that you really have a handle on quantum numbers if you can do all the quiz questions on them. Okay, down here, this electron. First, we're in level 5. Next number is 0 for S, right? And if you're in an S sublevel, the exact orbital is 0, and the spin on this is 1. Now, this is a D5. For D5, they would be all 5 up or all 5 down for our spins, right? We know they have to match according to Hund's rule. So if we do this electron right here, let's see, I'll put this one down here. We're in energy level 4. The next number, 0 for S, 1 for P, 2 for D. 2 for D. And then we could label these -2, -1, 0, 1, 2. So the only number that is going to be different is what orbital it's in, right? This electron right here, energy level 4. Next number, 0 for S, 1 for P, 2 for D. 2 for D, the exact orbital, -1, and the spin 1/2, right? The only thing different is going to be my third number for all of these, correct? It's in the same level 4, it's in the same level of D, it's got the same spin. So if we do this one, it's going to be energy level 4, 2, 0, 1F. I'm going to do that very well. 4, 2, 1. I don't know if that blue shows up a little bit. 1/2, and then 4, 2, 2, 1. Quantum numbers, huh? First time I ever taught quantum numbers, I taught them all. Way back, many I had to tell the students the next day it came through. Forget everything I said the day before. I don't remember. So that's pretty simple, correct? That's not bad. I mean, try to follow this. It seems, hopefully it makes sense. I think I presented it correctly. So there's some quiz questions on that that'll test you on the quantum numbers. Okay. Let's go to the next page here. If you grab this thing, here's something on quantum numbers here, but there's some videos in here. And it's great to get started. It's 12 minutes. Okay. Elements and groups, vertical columns of the periodic table exhibit similar chemical behavior because the elements in the same group have the same number of valence electrons. Same number of electrons in their valence shell. Going down a group, if we just talk about atomic size, going down a group, atomic size increases. Now, that is kind of an easy concept as you go down a group because you're gaining energy levels, right? Now, here's the word generally, because it is chemistry, nothing's 100%. Generally, going across a period or row, atomic size decreases. So when we get all done with these, we're going to go to our periodic table and we'll draw arrows to summarize this. So the amount of energy needed to remove the most loosely bound electron from a gaseous atom in its ground state is called ionization energy. Now, this is energy to remove an electron. Energy to remove an electron. Which elements don't want an electron anyway to become more stable? The metals on the left side, right? The metals on the left side do not want their valence electron. So, this is called the first ionization energy to remove the most loosely bound electron. Going down a group, ionization energy decreases. Now think about that. If you're going down a group, let's take group 1, lithium, sodium, potassium, rubidium, cesium. Every one of them lose their one valence electron. That valence electron is being pulled in by the positive pole of the nucleus. But obviously, if you get bigger and bigger and bigger, it should be easier to pull that electron away, right? It just gets easier as you go down the group. So as you go down the group, ionization energy decreases. Generally, again, we've got to put the word generally in here. Going across a period or row, ionization energy increases. They want that valence electron. Like they're trying to gain electrons, the nonmetals. Electron affinity is the energy change for the process of adding an electron to a gaseous atom in the form of an anion. Which elements want an electron? The nonmetals on the right, correct? The nonmetals on the right. Going down the group, the electron affinity increases. And going across the period, the electron affinity decreases. It should. So summary again, going down, the atomic radius increases. Going across, it generally decreases. So let's put this on our blank table, which is the next page. All right, so we are going to draw an arrow. Let's do this. I'm just going to put an arrow down right here, and then we're going to summarize it. Down a group. Atomic radius increases. It has to increase. You're adding more energy levels. That's just the radius of the atom. Now, removing an electron, ionization energy decreases. It's going to be easier to take an electron away going down the group. If you try to add an electron, electron affinity increases. Then let's draw an arrow across this way. We'll put it down here. From left to right. Across a row. We can put the word generally, again, it's not perfect. These are all generally. Atomic radius decreases. Okay, I'll have just some generalized questions on that, I'm sure. And there's a quiz question or two. Let's go to the next page here. And this is maybe not the prettiest stuff, but it'll work here. I'll update this a little bit here. Electron configuration notation of ions. First of all, this is the fluorine atom that does not have a charge. 1s2, 2s2, 2p6. What does fluorine want to do to become more stable? This right here, then, to become a negative ion is the same electron configuration notation as neon, right? This would be the fluoride ion. We know that nonmetals want to gain electrons to become more stable. What is the key? Having 8 valence electrons, because that's what the most stable noble gases are. Here's sulfur atom again. So this is sulfur, no charge. 1s2, 2s2, 2p6, 3s2, 3p4. This sulfur is going to gain 2 electrons to become the sulfide ion with this ending electron configuration notation, which matches the noble gas argon, right? Sulfide, it gains 2 electrons. Negative anions. Nonmetals. If we have metals, this is the sodium atom. No charge. By definition, an atom. Protons equals electrons. What's it going to want to do? It wants to get rid of that electron to form the sodium ion. It's still sodium. And this is the same electron configuration notation as neon, right? Then we have germanium. Germanium then is in the transition area here. Germanium actually has a +4 charge it takes on. So germanium's +4. This only shows it at a +2. If it takes on a charge of +2, it's going to get rid of these 2 electrons. But really what happens is it gets rid of those as well. So let's change this to a 4. Now, we have titanium. If we look at titanium, titanium can be a 4, a 3, or a 2 for an ion charge. 4, 3, or 2. What does it do most often? Become most stable? The 4 is bold, right? So it can lose 4 electrons, 3 electrons, or 2 electrons. This shows what it does when it becomes a +2 charge. It gets rid of these 2. And this actually shows iron's 2 charges. Iron can be 2 or a 3. So if iron gets rid of these 2, there's the +2 charge. If it gets rid of 1 out of the D, it stops. Because when you have a D5, that's my D5. That's pretty stable, right? So it stops. It doesn't take on a +4 charge. It takes on a +2 or a +3. Sometimes you can explain the ion charges with these half-filled sublevels, which are really stable. And then the next time it's chemistry, you can't trust any electron. That is, sometimes you can make logic, sometimes you can't. Okay, so let's see. Let's look at this down here. We have 2 electrons of helium have different values of ms, spin. That is, they have opposite spin orientations. We say their spins are paired. And the result is that the magnetic field of 1 electron is canceled out by the magnetic field of the 2nd electron with opposite spin. Elements and compounds that have unpaired electrons are attracted to a magnet. Such species are said to be paramagnetic. Substances in which all electrons are paired experience a slight repulsion when subject to a magnetic field. They are said to be di. Here's my pair. These are diamagnetic if they are paired. Think of everything's got to have double opposite spins. Think of the diamagnetic that way. Paired electrons. So I'll do some stuff like this, I believe. So give the electron configurations for copper 0, copper +1, copper +2. Are any of these species paramagnetic? How many unpaired electrons does each have? This is my 4s1 electron, right? So that's not paired. See, I'm paramagnetic there. And this, all of this is a D. (3D10), everything's paired up. So it's diamagnetic. And 3D9, we have one of them that's not paired. Okay. I'm not a fan of this. I guess it's in there, but isoelectronic. Not a big fan, but it's a concept that the boss tells me to cover, so we'll cover it. It just means ions have the same number of electrons, but different numbers of protons. One such series of ions is nitride, oxide, fluoride, sodium, magnesium. It is the same number of electrons. Same number of electrons. So if we start with sodium, let's start with sodium. It has 11 electrons. Right? We could put an 11 down here. It would lose 1 electron to become a sodium +1 ion. Magnesium, 12 electrons. It would lose 2 electrons to become a +2 ion. Fluorine, 9 protons. Oxide has 8 protons and nitride has 7. Then it gives us ionic radius. I wish what's missing here is atomic radius. So I'm going to add this in. I'm going to show you a pattern here. And I'm not looking these numbers up. I'll probably add this in here tonight for next semester. When you form a negative ion, the radius about doubles, closely to doubles. So the radius of the atom, the neutral atom here, I don't know, it's going to be about 73, and this is going to be about 70. Again, and this right here would be half of this, I don't know, 62. Actually be more than that, it'd be 60. Yeah, that'd be 124, so it'd be 60, 66. Again, forming a negative ion, the radius approximately doubles. Forming a positive ion, radius is about half. So this would be about 200 and this would be about 160. Again, it's cut in half. This is the, by atomic radius, this is the neutral atom, right? Atomic radius, neutral atom. All right, here's an odd question. Considering only ions with charges 1, 2, -1, 2, or neutral, give the symbols for 4 species that are isoelectronic with potassium. So first of all, what is potassium as an ion? It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1 is gone. So we need 4 that would have the same electron configuration notation. The neutral one is argon. Then, as we come over here, if calcium loses 2 electrons, it's going to have the same configuration as argon. So calcium 2 plus. If chlorine gains 1 electron, it's going to have the same configuration as argon, so chlorine. And if sulfur gains 2 electrons. All right, let's finish this up. The monatomic ion with a charge of -1 has an isoelectronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6. It is going to gain 1 electron. We'll finish this. We'll clarify this next time. This is all we got left. So on the quiz, you should be able to finish the quiz. I'll clarify this next time. We should be able to do everything on this quiz now. Please, 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 look at those quantum number questions. Look at the quantum number questions. You should be able to do everything on the quiz. I have your test up here if you want to look at your test.